So for today, we're going to solve now the t raised to n the t raised to n multiplied by EAT in a time function, which we will solve the equivalent value of that time function into the complex frequency function, which is equal to the n factorial over s minus a raised to n plus 1. So the Laplace of t raised to n e raised to at is equivalent to the integral of e raised to negative st multiplied by eat multiplied by t raised to n dt, approaching from 0 to infinity. So for this two having same base, so we can get the same base and then add the two exponents. So we're coming up with a minus s multiplied by t, which we factor out this value of this. So the integration of e raised to a minus s times t multiplied by t raised to n dt. So using integration by parts, we could solve this expression. So we will let our u as equal to t raised to n, and the derivative of t raised to n is equivalent to the nt raised to n minus 1 dt. So the dv is equal to e raised to a minus s multiplied by t dt, and if we integrate this one, we could get the v, which is equals to the e raised to a minus s parentheses multiplied by t over a minus s. So by plugging these variables in the equation of integration by parts, which is uv minus the integral of v du, is equal to t raised to n multiplied by e raised to parenthesis a minus s multiplied by t. So we're going to highlight them by t over a minus s approaching from 0 to infinity. So don't forget these limits, minus the integral of e raised to parenthesis a minus s times t and t raised to n minus 1 over a minus s dt. So if you're wondering how we get this 0, we plug in those limits in this equation. So we come up with a 0 answer because in the next, so in the here in this part we get the negative of this equation so that we could come up with a 0 equivalent. So or we get the negative exponent. So the n over s minus a multiplied by the integral of e raised to a minus s parentheses multiplied by t multiplied by t raised to n minus 1 dt. So this one is a non-terminating integral, so that's why we come up with this equation, which is the Laplace of t raised to n multiplied by e raised to at is equal to the n over s minus a multiplied by the Laplace of t raised to n minus 1 e raised to at. So we were going to set the values of n so that we can conclude that, or we can prove that this equation or this expression is a non-terminating. So at n is equal to 1, so by plugging in the values of n, so the Laplace of t raised to 1, or simply t, multiplied by e raised to at is equivalent to the 1 over s minus a multiplied by the Laplace of t raised to n minus 1, or t raised to 0 because of our n is equals to 1, and e multiplied by e raised to 80. So this t raised to 0 will be equal to 1. So 1, the equivalent of the Laplace EAT from the previous problems is equivalent to the 1 over SA. So 1 over S minus A multiplied by 1 over S minus A, sorry for that. So it's equivalent to the 1 over S minus A squared. So at n is equal to 2, the Laplace of t squared multiplied by e raised to 80 is equivalent to the 2 over s minus a multiplied by the Laplace of t raised to 1, or simply t, multiplied by e raised to 80, which is equivalent to the 2 over s minus a multiplied by 1 over s minus a squared, which is the value of our previous Laplace. So, t, sorry, 2 over s minus a multiplied by 1 over s minus a squared is equivalent to the 2 factorial of s minus a cubed. So therefore, we can conclude that the Laplace of t raised to n e raised to at is equivalent to the n factorial over s minus a raised to n plus 1. So that is the equivalent of t raised to n eat in the complex frequency function.